We are ready to start. So, of course, everybody knows Alessio, but still, I'm going to give an introduction just to embarrass him. So, as everybody, I guess, knows, he's the recipient of both the last Fields Medal and the EMS Prize. He's actually won several other prizes in his career. And let me just mention the Kurpe Co Prize and Stampacchia Medal and Feltrinelli Prize. So he's we're very proud that he's a former student of the Scuola Normale Superiore under the supervision of Luigi Ambrosio. He's currently at the ETH Zurich after being at the École Polytechnique and at the University of Texas, Austin, and at the beginning, even at the University of Nice. He's working on several different things. His celebrated works on optimal transport and the regularity of the Monge-Ampere equations, applications to functional and geometric inequalities, but also completely different subjects like Hamilton-Jacobi equations, KAM theory, semi-classical limit of the Schrödinger equation, the Perman-Lyons theory, you name it. And what is going actually to speak on today are some latest works on the obstacle problems. And without taking more of your time, I want to give the word to Alessio. Just please, if you want to ask a question during the talk, write on the chat or on the question and answers. And depending on the situation, I will decide whether to relay the answer at the end or to interrupt Alessio. Okay, please, Alessio.
Okay, so thank you very much, Camillo, and thanks to the organizers of the SIAM PDE seminar. So it's a pleasure for me to give this talk and also to see so many friends, although virtually. Yeah, so today I would like to present some recent results about the obstacle problems and in fact the generic regularity in this kind of obstacle type problems. My original plan was to use the tablet parallel to the computer. I had a small technical problem that I should manage to. So I mean, I apologize if maybe when I write now with the computer without the tablet, I will not write so cleanly, but I will do my best. So. So what's the topic about? Let me start with the motivation of this problem, okay? So the motivation of this problem that I would like to start with is the Stefan problem. So the Stefan problem is actually named after Stefan, although it was introduced before Stefan by Lamain-Clapeyron, 1831, is about the temperature distribution in a homogeneous medium when it undergoes a phase change. So let's think of ice, which melts, and then it becomes water. So in its classical formulation, let's say I have my domain, a cylinder, where I prescribe boundary conditions. So let's say the temperature of the water on the boundary. And then inside the domain, I have two media. So I have the ice and the water. These are separated by an interface, which is, of course, the transition interface, which is not prescribed. It's a boundary that we non-prescribed, we don't know, actually we need to study it. So it's called the free boundary. And in its simplest formulation, essentially what you assume is that the temperature, which is a function theta of t and x, so time and position, we're going to assume that it's zero inside the ice. So this is the simplest kind of Stefan problem, where essentially you just make the ice identically make the temperature of the ice to be identically zero. So this means that the temperature of the ice is not an unknown of the problem. So this is a simplification, but it's a very classical assumption. So that's why this is called actually one phase Stefan problem, because really the unknown part is only the water. So in the water, temperature is positive, as it's normal. And the way it evolves is through the most classical PDE that used to make temperature evolve, which is just the heat equation, right? So dt theta is equal to the Laplacian of theta. Now, this system as written in this way is not closed. The reason is that usually when you solve a PDE, you have to prescribe the boundary of your domain. But here, as I told you, the boundary is not prescribed, it's a free boundary. So I have to give you an extra condition, which kind of makes the temperature of the water interact with the free boundary. And this is called the Stefan condition. And the Stefan condition tells us that the derivative of the free boundary is given by minus the gradient of theta at the free boundary itself. So this means that every point on the free boundary moves through a very simple ODE, which is given by the gradient of theta. So just to explain, the picture you should have in mind is this one. So theta is not, one moment, sorry. So theta is not C1. So you see here is the interface ice water. I will click on that. Right. So this is the ice. Here is the water. And on the water, you see the temperature makes kind of an angle. So there is a discontinuity in the derivative of theta. You take the derivative of theta inside the water, and you flip the sign, right? So let's say you compute the derivative outward, and then you flip it inside, so that it actually points now inside the water. So the gradient of theta points outside the ice, and then minus the gradient of theta points inside the ice. So you see that the free boundary, which is this curve, will move, and it will move always shrinking the ice. And that's normal, right? Because I'm assuming theta to be non-negative, because it's 0 inside the ice and it's positive outside. So of course, in a non-negative environment, there is only melting and there is no freezing. So there is only one possible direction. So the ice melts. So you see that the gradient of theta minus the gradient of theta always points inward. Okay, now I told you that I wanted to solve obstacle problems, and the reason why there is a connection is because actually Stefan problem and obstacle problem in this setting are more or less the same, and I will explain this to you. So there is a change of variable introduced by Baiocchi and Duvaux in roughly 1972, where you consider the function u of tx, which is the integral from 0 to t of theta. So a nice, let's say, remark that I noticed is that when I asked to people in Italy, some people told me that this is the Duvaux transformation, and when I asked to people in France, they told me that this is the Baiocchi transformation. So this is the one instance where French give credit to Italians and Italians give credit to French. So I give credit to both. So they did it in slightly different settings, but essentially the idea was more or less at the same time from both of them. So anyhow, this is the transformation. You can think of it as a simple change of variable. Oops. And you see that with this transformation, dtu is nothing else but theta itself. So dtu is the temperature, which is non-negative by assumption, and u is an integral of a non-negative quantity, so it's non-negative as well. So u is non-negative, it's increasing in time, and also it solves the following PDE. dtu minus Laplacian u equal minus the characteristic of u positive. So this is not completely obvious. You need to take the previous equation, Stefan, the Stefan problems. So the dt theta is Laplacian theta, and then the boundary condition. You integrated that in time, and you need to compute then the Laplacian of these quantities. As you can imagine, the fact that the theta makes a corner at the free boundary will create some kind of some singularities, and that's responsible for this discontinuous right-hand side in there. So the computation is not, let's say, immediate, but it's not too difficult either. Oops, that's the problem with when I do this with the tab, without the tablet. But let's note that this right-hand side, so this is minus the characteristic of u positive. So this is the function which is 0 where u is 0, and this minus 1 where u is positive. So this is trivially L infinity, which implies that u, by parabolic regularity, u is C1 in space. As a consequence, you're solving heat equation with bounded right-hand side. So you get, by just parabolic regularity, C1 regularity in space of the solution. Why this is important? Because now you have a function u which is non-negative, and where u is 0, well, u is 0, but where u is positive, it satisfies dtu minus Laplacian u equal -1. Okay? And so you see the kind of situation is the following. So here is u equals 0. And with this change of variable, this is still corresponds to the ice. So u equals 0 is the same as theta equals 0. If you, it's not complicated to see because you see that because u is increased, is this integral of theta. The moment, you know, either you are inside the ice all the time, but since the ice is melting, you can check that they are the same set. So this is a consequence of the fact that the ice is melting. So either you are, if you are in the ice, you were in the ice in the past. And this kind of fact, it tells you that the free boundary hasn't changed under this change of variable. But here, the fact that you see the gradient of u is 0 at the interface, so here there is no angle anymore. This is a consequence of the parabolic regularity I mentioned to you, right? Because u now is C1. So because u is C1 and u is non-negative, the gradient must be 0 at the minimum. So here, then we have an extra condition that the theta doesn't satisfy. So the gradient of u now is 0. And now here outside of the contact set, we have dtu minus Laplacian u equal -1. So this condition is actually telling us that now u solves a overdetermined PDE because on the free boundary, not only u is 0, but also the normal derivative is 0. So it's at the same time it's solving Dirichlet problem and a normal problem. So this is an overdetermined problem, and this overdetermination is what governs the actual evolution of the free boundary. So the free boundary evolves in time to make sure that at every instant of time, you will satisfy both Dirichlet and Neumann condition on the free boundary. This problem has existence and uniqueness. Actually, is a simple. One can prove it as a like as consequence of gradient flow of convex functionals. There is a nice convexity principle here. So the existence and uniqueness is not an issue. The question is regularity. I mentioned this as an obstacle problem. Why obstacle problem? So I will explain this to you, but let me just tell you what are the natural questions. So the natural question of this problem is the regularity of u and the regularity of the interface. So the regularity of the solution, regularity of the free boundary. And to be honest, the regularity of the solution here is not even the goal, because u is not even the original variable. Really what matters here more than everything else is the free boundary regularity. But okay, then in fact, it's also true that if you say something about u, then dtu is theta, and then you can say something about theta. But let's say the derivative, so these are both natural questions, but the core is the free boundary. Now, in this, most of this talk, 99% of the time, now I will go to the stationary case. So I will drop time and look at the elliptic problem. And then I will mention at the very end, what can you do in the parabolic case. So elliptic case, what is the elliptic problem? Just take the same PDE as before, but drop time. So now u is a function only of position, and then the PDE becomes this one. So Laplacian u is the characteristic of u positive, and u is non-negative. Here you can see the same picture as before. So you have a function u which is 0. It satisfies Dirichlet and Neumann boundary condition on the free boundary, and then it has Laplacian 1 outside. So this problem is called obstacle problem, as the title says on the top, for the following reason. So look at this energy. This energy is just Dirichlet energy plus V, so kind of a potential energy with Dirichlet boundary conditions. What does it mean? What does it model? So you have to think of this. So here you have a kind of a wire. So this is, let's say, V equal to F. And to this wire is attached an elastic membrane. Okay, so this is the graph of V. And so this elastic membrane, let's say, minimize an energy, which is a sum of two terms. This part is the elastic energy in inelasticity. So this is the elastic energy of the membrane represented by the graph of V. And this term V represents the gravitational energy. So here you have to think that I'm putting the gravitational constant G equal 1. So I'm just normalizing gravitational constant. So I have potential energy plus kinetic energy. But then I'm adding a condition here, V non-negative. So the point is the following. You have your membrane, let's say, that a priori would like to be like this at equilibrium. So it's attached to the boundary, and then the gravity acts, and so the membrane bends. But then in reality, there is a line below. So there is a table here that acts as an obstacle. And the membrane is not allowed to cross the table because, well, physics. So the membrane in reality is not allowed to do this. So this would be the configuration if there was no table. But in reality, there is a table. So in reality, the membrane will do something like this, where it will touch the table in some region here, and then is detached somewhere else. So this is called the obstacle problem, exactly because we are minimizing some kind of energy type, elastic energy type function with gravity acting, and then the table acting as an obstacle from below. If you write the optimality condition for this problem, you get exactly this system. Okay, so this equations is nothing but the Euler-Lagrange equation for this variational problem. And so that's kind of the picture, okay? So the gravity is pushing down and my membrane cannot cross the table. Therefore, where you see where the membrane doesn't touch the obstacle is a critical point of this energy. This term gives you Laplacian, this term gives you the 1 here in this equation, Laplacian u equal 1. And then where u is 0, u is 0. There is nothing to say. Okay, so this is why it's called the obstacle problem. I showed you that this problem arises in two different ways, either as a minimizer of this elastic energy or as the stationary version of the integrated version of the Stefan problem. Stefan problem, you integrate the variable from theta to u, you make it stationary, you get this one. But so you have two different way of getting this problem. And so now we focus on this PDE and we ask ourselves, what can we say about the solution? Okay, so about you, by now we know essentially everything. In particular, it was proved roughly 50 years ago, then the Hessian of u is bounded. Okay, so this is optimal because you see that the Laplacian of u is discontinuous, right? The Laplacian of u, I told you, let's go back here. You see the Laplacian of u is equal to 1 here, outside in the water. And then the Laplacian of u here is 0. Where u is 0, the Laplacian is 0. So the Laplacian has a jump. So the Laplacian is discontinuous, so the Hessian cannot be continuous. So the best we can hope for is bounded, and that's true. So the solution has bounded Hessian. Good. Second thing, quadratic growth. So if you take any free boundary point, so point at the boundary between ice and water, or let's say the contact point of the membrane, or let's forget about ice and water now, on the free boundary, u, okay, is 0 at the free boundary, but what is important is the sup of u over the ball of radius r goes like r squared. So you take the free boundary, you take a small ball of radius r around, and then the solution roughly behaves like this, grows like r squared in a scale r. So the kind of growth of the solution is like the one of a parabola. Is a parabolic scaling, right? R squared growth. Okay. These properties have been proved first. Okay, the optimal regularity was known already by Frese in the 60s, as I said, and then the optimal regularity was the beginning. This quadratic growth was noticed by Caffarelli, that then was the beginning of the free boundary regularity. So let's say that the regularity of the solution is this one, and that's everything I want to tell you. But once I have this, I can start to analyze the free boundary regularity. How do I do it? By blow up. So I'm going to take a free boundary point. I'm going to start to rescale u around the free boundary and try to understand how u behaves under rescaling. So the idea is the following. So you see, I have u in a very, very small ball, and I want to understand how u behaves near a ball. Since I want to get r go to 0, but I want to get something non-trivial, what I do is that first I do a rescaling. So I make the ball of radius r a ball of radius 1. I zoom. So this is what I'm doing in this inner rescaling here, right? So I do a translation to make x0 the origin and a dilation to transform the ball of radius r and a ball of radius 1. And then I divide by r squared, because I told you that here in BR u behaves like r squared. So if I divide by r squared, now I get something of size 1. Okay, so with this scaling, I trivially have that these rescale functions are all 0 at the origin, and they're all of size 1. And now by compactness, I will get to get a limit. But if I need compactness, I need a bit of regularity estimate, like something that, like Ascolar-Zeta theorem, that tells me that a limit exists. How do I get compactness? Here is actually very easy, because you can notice that because of this R, every time I differentiate these rescale functions, so if here I start to get derivatives, k derivatives, I will have powers of R kicking out every time I differentiate. And particularly if I do 2 derivatives, I will get r squared coming out that we cancel the r squared at the bottom. So the Hessian of the rescale functions at a point x is equal to the Hessian of my original function u at a different point. But the Hessian by assumption was bounded. Well, not by assumption, by optimal regularity was bounded, I told you before. So the Hessian of all my functions is bounded. So I have a family of functions which are 0 at the origin, the sup in bolus 1 is of size 1, and they're bounded Hessian. Therefore, they're compact in C1 by Ascolar-Zeta theorem. So I can take a limit. And now I ask myself, what can I say about these limits? So this is usually, so the fact that you can take blow-ups, it's very classical. In many problems, you can do this. The difficulty is, can you classify blow-ups? And then once you classify them is, can you get something out of them? Okay, so the blow-ups essentially are all the possible shapes that you get when you look infinitesimally at your solution around a point, right? So you're blowing up and you look at the limit, which is like really the infinitesimal shape of your solution. Okay, let's make some educated guesses of possible blow-ups. First educated guess. Let's assume that my interface is nice, a nice analytic upper surface. And then I have 0 on the left, positive on the right. Then my solution will look like this. Then I start to blow up. As I blow up, my upper surface, the interface, will become flatter and flatter, just because by assumption this is smooth already. So in the limit, I will get a hyperplane. And then I told you that it behaves like something quadratic where it grows. So in the limit, I will get something like this. I will get a function. So the interface becomes flat, high hyperplane. On the left of the hyperplane, my solution is 0. On the right, E behaves like a parabola, right? So E is like a unit vector here in this direction. And then I have E dot x positive part squared on the right, so 1 alpha squared, so that this function has Laplacian 1 here, is 0 here, and it has flat interface. So this is what I expect to see every time I blow up around a nice boundary point. So I give a definition. I say that x0 is a regular point if, up to a subsequence of radii, the solution converge to something like this, something of this form, like one-dimensional function. This is just a definition so far. Second educated guess. So the second option is that the free boundary looks something like this. So very tiny. Then my function will look something like this. As I rescale, the contact set becomes flat, thinner and thinner. In the limit, I see a parabola on both sides, something like 1 half E dot x squared. Of course, this is just one possibility if I am like in dimension 2, like in this picture. If you are in dimension n, it's more complicated because I could get any quadratic function in some sense, right? So anything which has 1 half AXX would be a possible limit just because it's a solution itself. So you see, so I will say that x0 is a singular point if my limit of my blowups is a quadratic polynomial And notice that this polynomial will be of the form 1/2 AXX, where A is non-negative. So this is due to the fact, remember, that my solutions are non-negative. So P will be non-negative because it's a limit of non-negative function. And then trace of A is 1. This is because the Laplacian of P should be 1, because my solution U has Laplacian 1 outside of the contact set. Under this scaling, the Laplacian remains 1 outside the contact set, and in the limit, the Laplacian of P will be 1 outside of the contact set, which is a set of measure 0. You see, for this polynomial, the contact set is just a lower dimensional set, is a line or a hyperplane or a k-dimensional space. So any limit like this is a possible singular point. Okay, so just to give a picture, so let's say in 3 dimension, I could have maybe a contact set that looks like this. So this is just the same picture as before, right? Something like very flat on this line, and then I added one extra variable. So it's the same picture as here, where this contact set in 2 dimensions, and then you just add a third dimension orthogonal. So that's an option. Or maybe the contact set could be this. So in this case, you see in the left, in the limit, the contact set will become a plane, 2-dimensional plane. Let's say something like x2 equals 0, for instance, in some system coordinates. And then my polynomial would be the polynomial that vanishes on x2 equals 0, which is this one. Or maybe my contact set looks like this. And then in the limit, my solution will vanish on a line. So the x3 axis. And then maybe the polynomial is something like this. Well, I'm not sure it's this one. Now I have much more choices. Could be, I don't know, 1/2 x1 square. Well, no, 1/2 is not possible. 1/5 x1 square plus whatever number x2 square, so that the sum, the trace is 1. So just to say that, okay, here I wrote 1/4 for symmetry, but it could be something more complicated. But okay, so you see that the picture gets more and more complicated as the dimension increase. So in 2 dimensions, you only have the contact set will always be a line, but in 3 dimensions, it could be a plane or a line. In n dimension, it could be any k-dimensional hyperplane for every k. Okay, I gave you 2 definitions, and it has been a fundamental theorem of Caffarelli of 77 that these two options, singular and regular point, exhaust everything. There is nothing else left. So Caffarelli in 77 proved the following. Let 0 be a free boundary point, then one of these holds. Either 0 is regular. Remember, regular means that up to a subsequence, I converge to a half space solution. In this case, the free boundary is analytic in a neighborhood. So then it's as nice as you want in a small neighborhood. Or 0 is singular, in which case the free boundary gets thinner and thinner. So I will explain this in a picture, something like this. So either you are, the picture is like on the left, nice analytic upper surface, or you have the free boundary looks like here. So there exists some unit vector ER, depending on the scale R at which you look at, such that the free boundary is trapped in a little of our neighborhood of this hyperplane, the hyperplane orthogonal to ER. Okay? So this is what Caffarelli proved in 77. So you see that on the regular points, essentially he said everything. Regular points are analytic. But on the singular ones, still there are questions. And let me explain this to you. So at singular points, that's the picture, right? And now there are 2 questions that you may ask. First of all, this direction ER in the theorem may depend on R. So there exists a direction such that the free boundary is very close to this hyperplane. The theorem of Caffarelli in 77 didn't rule out the possibility that the vector changes with R. So this is usually a very delicate problem in even in geometric measure theory, where maybe you have something, a spiral, a logarithmic spiral, and as you zoom in, the free boundary start to get flatter and flatter, but the hyperplane at which is converging changes with the scale, maybe rotating very slowly around the point. So in general, it's not so, there is no cheap way of proving that this doesn't happen. It's usually a very delicate point. Second, the little of R comes from a compactness argument, so it's not quantified. Okay, so let's look singular points. From now on, sigma is the set of singular points in the free boundary. These are the only one I care about. And there have been a series of work, first by Caffarelli and Rivière in 77, then Sakai in 91, both these theorems are two-dimensional, and finally by Caffarelli in 98, where they proved the fact that the limit of view at every singular point, as you zoom in, the solution converges to a polynomial, so the limit exists. So let me remind you that at singular point, I told you the following. A point is singular if up to a subsequence of radii, I converge to a polynomial. So the theorem is, the definition is up to subsequences. What Luis Caffarelli proved is that the limit is independent of the subsequence. And this is really the key information one needs to say that the vector ER that I told you about doesn't depend on R. So the limit is independent of the sequence. Moreover, he proved that the map that to every free boundary point associate the Hessian is a continuous map. So let me just make a comment probably about this. So this statement, you can look at this saying that U of x0 plus y is equal to p star x0 y plus little o of y square, okay? So if you look at it in this way, this p0 star plays the role of the Hessian of u at x0 applied to y, maybe with one half in front. If you think of a Taylor expansion, right? So I'm telling you that, so this p star is really the second order Taylor expansion of u, in some sense. In some sense, just because u is not differentiable, is not C2, and also this singular set where this polynomial exists is not an open set, so I cannot say anything in particular. But I'm saying this polynomial behaves like the Taylor expansion, is essentially second order Taylor expansion. And the second condition, the fact that he proved that this polynomial is continuous, is like saying that the Hessian of u on the singular set is a continuous map, formally, in some formal sense, okay? Very good. And then, out of this information, as a corollary, Caffarelli proved that sigma, so the singular set is contained in a C1 and minus one dimensional manifold, okay? So, I will not prove this result for you, just not for sake of time. What I would like to discuss is just one thing in the implication. So what's important here in this implication is the following. So if one looks at the proof, what the proof shows is that this kind of, the fact that u is close to p like little over square implies sigma C1. So you see, and remember the polynomial varies continuously. So this is kind of a C2 regularity assumption on u, and this implies a C1 regularity assumption on sigma. So you go one derivative down. So if you check the proof, you can immediately realize that if here you can put a power r to the 2 plus alpha, then you can put C1 alpha regularity for sigma. So you lose one derivative. Okay, here I just wrote down what the definition of CK alpha space is. So this is one important fact, right? If I improve the rate of convergence to the polynomial, I improve the regularity of this set. Now, let me make a comment. Here, alpha, the best alpha you can hope is 1. Just because you see, if u was even C infinity, and I subtract the second order Taylor polynomial, I will see the third one if I'm C infinity. So, I mean, even for C infinity function, this behaves like a third order polynomial. So I cannot hope to say that this is better than R cubed, even for smooth functions, right? So the best alpha I can hope to put here in general is 1. Okay. So, so my goal is to understand the free boundary, in particular the singular set. And by this implication, if I can understand better how U converge to this polynomial, I can understand better the structure of sigma. Now, in 1999, Weiss introduced a very powerful monotonicity formula. And what he proved is this following theorem. In 2 dimensions, he showed that the convergence holds with some power alpha. So he proved that the convergence R to the 2 plus inverse alpha. And as a corollary, he proved in particular that the singular set is contained in a C1 alpha curve. So when Weiss proved this theorem, actually, if you look at the paper, almost all the paper is in n dimension, and then there is one particular step where it needs 2 dimension. And so he actually tried for quite some time to understand whether he could make the proof work in every dimension. But you know, it's the kind of things that you feel like, oh, I'm almost there. I don't know how to do it, but it feels so strange that it's restricted to 2D. But only with 2D I can conclude the argument. It's really one small part of the paper where he cannot do it. So, so he told me that, yeah, he really hoped he could prove this in every dimension. He didn't succeed. He gave up. He proved this. And so this question, whether anyhow you could push it to 3 and higher dimension, remained actually. And this was his approach was actually extended almost 20 years later to every dimension by Columbus, Paul, and Velichkov. And what they could prove is the following result: that if you are in dimension 3 and higher, you can actually make Weiss proof work. Essentially, where he was doing some compactness argument, they made it quantitative. So for for people who are experts, it's about doing some. What Weiss did was kind of an epiperimetric approach, and there was a moment where he had to construct the competitor, and there at some moment use a compactness argument. While in their approach, Columbus, Paul, and Velichkov, they can really do an analysis of the modes on the sphere, and then they write the comparison more. They really do an analysis, and they don't use compactness. They can really construct a comparison. And they can do in this way make the approach work, but there is a catch. They cannot get a power, they can only get a log improvement. So they prove that they can improve the R square, but they only get a log R to some power, negative power epsilon. So in particular, sometimes the sigma is a C1 log epsilon manifold. So it's C1 with a log epsilon modulus of continuity. At the same time, more or less, where they were trying to do this, I was also looking at the same problem with Joaquin Serra here at ETH. And what we realized is that we had a similar problem as them for different reasons. But as we were trying to prove this convergence, there were always some moment where we cannot make the proof work. At some moment, we just decide to give up because we say, okay, we cannot make the proof work. But then we realized that maybe the proof where we cannot make the points where the proof failed, we could at least estimate them. We could say, well, they're not that, it doesn't happen that often. So the kind of results we managed to prove in 2019 is that, in fact, you can prove a better result, actually C11, so you can get 1 power more, but you have to give up a set of codimension 3. So what we prove essentially is that up to a set of codimension 3, you get cubic convergence. In this in particular in 2 dimensions, n-3 is -1, so it's empty. So this gives you C11 unconditional in dimension 2. We also get, in the way of our proof, the same log epsilon regularity of Columbus, Paul, and Velichkov, but for different reasons, without the epiperimetric. And let me mention that the n-3 is sharp. So in dimension 3, you can construct a solution to the obstacle problem where the log epsilon convergence happens. So there is really, so you cannot improve that logarithmic convergence. So so Weiss theorem, it was false from dimension 3 on. So it wasn't him who couldn't prove it in dimension 3, just you cannot put a power in dimension 3. Okay, so this is what we proved. Actually, this was concluded roughly in 2017, to be honest, published a bit later. And then at the same time, we ask ourselves, okay, but this singular set is there. it's a bit annoying, right? Because there is, first of all, maybe I should re-emphasize one crucial thing, right? I told you the following, right? Let's look at the statement. I told you the singular set is contains a C11 n-1 dimensional manifold up to, say, codimension 3. Let's forget that. But you see, we are in dimension n. The free boundary is n-1 dimensional. And then I'm telling you that the singular set is a n-1 dimensional manifold. So the singular points are as large as the regular points. So my free boundary is split in regular and singular, but it's not that singular are smaller than the regular. So we're talking about two sets that have the same size still. And there is nothing you can do about that, right? Even in 2 dimension, you can think of this example, right? A drop, then a line, and then a drop. So the contact set could be this. All these points here on the drop here and here are regular, but this segment connecting them is singular. These are the singular points. And then outside this set, you have Laplacian u equal 1. So you see, this is one dimensional, and the boundary of these drops is one dimensional as well. So fine, we cannot say anything. But then, so we started to wonder whether we could say something in a generic sense. And then we come to the title of the talk, right? Generic regularity. So this is, there is the following conjecture that I will state for you, the Sheffer conjecture. And to state it, let me introduce the following setting. So we are looking at the obstacle problem again, but let's remember that U has some boundary condition F. So what you could think, right, is that, okay, for this boundary condition, I could have some singular set, but maybe if I start to move a bit my boundary data, the contact set will change, and perhaps the singular points will disappear. And that's actually what Schaeffer conjectured in 74. He conjectured that for the F generic, the singular set should be empty. So let me say that Schaeffer didn't really say what generic means. Generic in the sense you like. And I will give you a definition for what is for me. So for us to try to attack this problem, we will introduce a one-parameter family. So this conjecture has been around for roughly now 45 years. There has been a result in dimension 2 given by Monod. So it could actually prove Schaeffer conjecture in dimension 2. So to attack the problem in every dimension, what we did is the following. We consider one-dimensional family of obstacle problems. So we take boundary data indexed by parameter t. So t, you can think of it as a time, but it's really just a parameter in the problem. And we are going to assume that the boundary data are monotone increasing. So we assume that dt partial t of ft is positive where f is positive. So this is just to avoid that you take the same boundary datum for every t. So you're not allowed to cheat and take a one parameter family that is actually independent of t. So this is really moving, and we make them moving monotonically. It's convenient. And then we consider ut the solution of the obstacle problem with boundary data ft. And the reason why we write in this way is because for n equal to, ut is actually the integral of the pressure in the Illyshov flow. So it's actually a setting which is compatible with the Schaeffer conjecture, but it's actually also come from Illyshov. And so let me consider sigma t the set of singular points in the free boundary. So for each t, you have sigma t the set of singular points. And then I consider sigma to be the union of all the singular points. So the idea is this. I have my solution for each t. So I have one parameter family of singular solutions, one parameter family of solution to the obstacle problem. And these are increasing in time. So they are ordered by comparison principle, they're one above the other. And each of them has a singular set. And then I take the union over all the singular sets. So this is an uncountable union. And I want to analyze all the singular sets together. The idea is that every time I know something about one solution for a certain t, I want to extract information on a different solution. So I want to use that they're ordered in t to kind of let them talk to each other. If I know something about one, I can say something about someone else. So embed each solution is one parameter family of solutions. That's the key idea. And what we did, together with Xavi Ros-Oton and Joaquin Serra, we proved the following results. Well, I will give you the consequences later, but I think this is one of the key results. So inside this huge set sigma, there exists a subset sigma star, which is very good. It actually covers sigma up to codimension 2. And what happens in sigma star? So let's assume that 0 is in sigma star. So, okay, the sigma star, just ignore it for a moment. This is just a good set inside sigma. So if you forget this, let's think that 0 is in sigma of T0. So the picture is like maybe something like this. Oops, let's see. Right, so this is my singular point. And this is UT0, okay? Which is 0 here and is positive outside. Okay, now what we prove is that for any epsilon positive, UT0 has an expansion up to order 5 minus epsilon. So we, in my previous theorem with Joaquin Serra that I stated, we proved that U minus this polynomial was capital O of R cubed. Here we prove that we can subtract 2 more polynomials, one of degree 3 and one of degree 4, such that we have an Taylor expansion up to order 5, almost. And then, as a consequence, we prove this. So let me try to, this is one of the key facts. So by the expansion up to order 5, again, I draw here, let's say this is my contact set for U at time T0. What happens? So you have to think the following. This is U at time T0, and the boundary data are increasing. So suppose that you start to raise the boundary datum. So you add here plus T, a small t. Then what will happen is that your solution will lift in time, and this point, so the contact set will become smaller because they're ordered, so one is above the other. So let's say the contact set for U of T0 plus T will be smaller, will be somewhere here, right? So let me just draw. This was the original contact set of U at time T0. I'm zooming in. So just this set should be the same as this one, just I'm doing it again. And then this is the contact set at time T0 plus T. So here, so essentially by lifting, I cleaned a small ball around this point. So here, this ball is now clean. And the question is, how large is the radius of the ball as a function of T? So if I lift by T, how much I clean around this point? And what we prove is that you clean essentially T to the 1/4. So R here is like T to the 1/4. And 1/4 is not surprising because 4 is 5 minus 1. Okay, so this is really 1 over 5 minus 1. Very good. Of course, if here you put, I don't know, 10, then here you would have, this 4 will become 9. So you could improve the power. But this is not the end of the story, right? So here I just proved that a cleaning property, which you see is telling me that these sets are not independent of each other. If one point is a singular point for one, then it tells me that the singular points for all the others cannot be wherever they want. They have to be actually far away. So this is kind of an order 4 rectifiability property from the future, in the sense that I'm telling that I'm cleaning a power 4 from above. If you think of this as a manifold in space-time, I have kind of a cleaning property from above of power 4. But this is not the end of the story because of this set sigma minus sigma star, which is codimension 2, and this is too large for us. So we actually need to give a very precise description of this set up to codimension 3. So this is another part of the story, which is actually kind of involved. But let's say once you put all together, I tell you what's the result. We get the Sheffer conjecture in dimension 3 and 4. More precisely, we prove that in dimension 4, sigma t is empty for almost every t. And then in dimension 5, sigma t has dimension m minus 4 for almost every t. So this is the result. And okay, again, the 4 is not surprising, I guess, because of this 4 that I got before. So you could ask me here, okay, but then if here you could put a power 10, then here you will get 9, and perhaps you could prove the result up to dimension 9. So you stopped at 4 because you have been lazy. Not really. So there is also all this part, and here n, the dimension less or equal than 4 is crucial. So in the other one, if you improve the power, you can go higher. More. You could go higher, but you still have these points which you need to deal with, and there you really are stuck at 4. I will be happy to say more if people have questions. But so this is the elliptic case. And what about the parabolic case? Because this was the original one, right? So in the parabolic case, you would like to do similar, right? I have Stefan problem, and you see, I use the t variable in the Sheffer with the idea that if I'm able to understand Sheffer with variable t, then having Sheffer with a point parameter variable like t, it should be similar to do Stefan problem, where t now is the time in Stefan, right? Because I have elliptic problems where I drop the time and then now I added one variable just as a parameter. Perhaps understanding Sheffer with t should be similar to do Stefan where I have time, naturally. That was actually our hope when we also started to work on the parabolic case. And this is still a work in progress. And in fact, sometimes the structure that I told you kind of extend. And maybe I don't want to enter too much, but we really thought for very long that essentially, if we could understand like Sheffer, we could just kind of redo that in Stefan. Until we realized that it doesn't work. It doesn't work at all because just is false what I said in the elliptic problem, instead in the parabolic setting. The reason is that actually this is, so what happens actually is that if you do in the Stefan problem an expansion, you can say that u is like a polynomial, 1/2, let's say, e dot x squared. This is true. But then you get the third order term, right? Let me call it q3 of x and t, plus something, let's say. Oops. This one is not, so then the analog of what I said before would be, oh, then you have before I told you, you have an harmonic polynomial here. So the analog here would be, I have a caloric polynomial here. That's false. This function looks something like, so it looks something like this. This function is actually a caloric polynomial. So let's say something, maybe I should say like this. So let's say here I have, let's say 0, 0, I have time and space. This is x and this is t. This is my point at 0, 0 in space-time. This is the past. And essentially, if you go in the past, you have the ice melting, but the ice melting, so this is the ice at time t. But the ice melting here, it cannot, it cannot disappear. So it really has a contact set. So you cannot make this volume, this region of the ice melting too small. The point is that really here there is a definite speed of the interface. And so here around this point, like if you look in a parabolic domain, so the rational scaling would be like r squared, okay? So in a parabolic scaling, maybe I should do it again because it's not very obvious. So let's say this is r and this is r squared. Then if this is a point where the ice disappear and you go back even in one dimension, the ice will be everywhere here. So the speed is like of order 1, the speed of the ice melting, right? So this is the ice, the separation ice as water. This is space. This is time. So you see that the contact set in a parabolic region, it's there. There is always, this volume is r cube. There is nothing you can do about that. So because of this r cube volume, it's not true that u is close up to power 3 to a caloric function. It's just definitely false because there is in this region, the function is not caloric. So this means, in reality, two things. It means that, first of all, this function cannot be caloric at all. It will be caloric here in this part on the right, and it will be caloric on the left. But it will be a kind of layer in between, which has a definitive volume, even in dimension 1. And in particular, if you think that you can try to analyze by perturbing around solutions of, in the elliptic case, we did it perturbing around elliptic polynomials. What we used all the time in the Sheffer was kind of monotonicity type formulas. So we linearize our problem around an expansion which looks more and more like an harmonic function or expansion to harmonic functions. But here, the moment you are order 3, you are not caloric anymore, which means that every monotonicity formula you may have in mind for the heat equation just fails here. And it breaks down at power 3. But if I think what I needed to prove my theorem here, I really needed to reach power 5. So the theorem here, it worked because I reached power 5. But here, already at 3, I'm stuck, because at 3, I cannot go further. So the approach to study the Stefan problem is actually, the approach to study this Stefan problem is completely different. The moment you are at 3, you need to come up with another idea, because just you cannot treat it as the Sheffer conjecture. Just the two problems diverge, even if they look very similar. And that's why this is still a work in progress, because we had to actually work much more on this than we expected to. So we finished by now the Stefan, the Sheffer paper by more than a year, and we were working already on the Stefan before, but this is still work in progress, and now things are all converging. And what we can prove, so we can kind of extend the theorem. I will not enter into details, but then by analyzing the free boundary in the Stefan problem, what we get as a corollary is that in 3 dimensions, the set of singular times, so the set of times where you see singular points, these are actually dimension 1/2. So this means that you see for almost every time you have no singular points, and then if you have no singular point at one time, you will have no singular point in a neighborhood just by continuity. And then sometimes you may encounter singular points. These are a closed set which have dimension at most 1/2 in dimension 3, which is, let's say, the physical dimension of the Stefan problem. And there are very famous problems where this dimension 1/2 appears, and is a very important question: does these singular points even exist? In the Stefan problem, they do exist, and actually I can show this to you with this picture. So here you see around this point, here, if you look around this point, right, you have this neck of ice, which is melting. And if you wait a bit of time, at some moment this will completely melt, it will pinch, and then these two blocks of ice up and down will kind of separate. So there will be a change in topology and everything. And so the singular point is there, it's happening, so they exist. So I stop here. Thank you for attention, and you're more than welcome to ask more questions about whatever you want about the talk. Thank you.
Thank you, Alessio. And I invite everybody to make a visual applause. So questions are open, and I see there are actually already 2 in the question and answer session. So first of all, a question by Delio Mugnolo. And the question is, are you aware of any application of heat kernel theory to study regularity issues for Stefan problems?
Well, so depends what you mean by heat kernel theory, but in some sense, the point is that if you want to understand the solution of the Stefan problem, around the free boundary, as I said, up to power 3, in some sense, your solution kind of look more and more like, so below power 3, it looks almost like a caloric function. So you have this polynomial first to subtract, but then the contact set is like a cube. So until you look at power 3, with below homogeneity 3, it looks like caloric. The moment you reach power 3, this breaks down completely. And that's where the difficulty starts. So then you cannot think of it as anymore as a kind of a heat problem. But the difficulty, so in one dimension is actually very easy, the answer to the problem. And if you look at 1D, what you will do is the following. You arrive here in this situation, but if you're in 1D, you just make a very simple comment. You say, okay, but wait, here, the ice in one dimension, if here it's a singular point, in the past, this is a positive speed. So what happens here on the right is completely independent of what happens here on the left, because they're disconnected. In one dimension, 1 point separates. Let's say this interval then separates. Which means that this, so in some sense, I cannot know what happens on the left. So this point, so this, if you just localize the problem to this rectangle, let's say, here, the right rectangle, you cannot realize that this is a singular point if you just look here, because you don't know what happens here on the left, it's unknown to you because it's on the other side. Which means that this is like a regular point. So here in reality, this is a fake singular point. So you can treat it as you treat regular points. And actually, you can prove that you are analytic on this side. The same way you look at this rectangle, and then you prove that you're analytic on the other side. And then you have two nice analytic expansions that they hold up to 0. Then once you reach 0, these two analytic expansions, you stop there. These are positive analytic functions on each side. And then you just start the heat equation starting from them. So the solution is monotone, so you just start the heat equation with that as initial data, and that's the solution. So actually in 1D, this kind of picture shows that it's very quick. But it also tells you something, that the moment you are at configuration like this, you have to think that the singular point behaves like two regular, so each side of the singular point behaves like two regular points. Of course, this argument is very quick in one dimension, but now if I am in n dimension, you know, I could have these two fronts of ice meeting, but it's very difficult to show that what happens to the right doesn't influence what happens to the left, because, you know, I don't know how to interface with meet. Maybe they meet at 0, but then in reality, if I look a bit of the past, I mean, it's not. I mean, I'm not saying that I have a hyperplane. I'm just knowing that there is one point where two blocks of ice meet, but who knows in the past whether the two blocks of ice see each other. For instance, if instead of two-plane solutions, I would have a conical solution, so the ice is shrinking like a cone around the point and around the tip, then there I can see all around, because a cone in 3 dimensions doesn't disconnect. Because if you take a cone and you take the section for each time, I get a circle, which doesn't disconnect. So that's why the problem becomes much more complicated from dimension 2 on, and that's what we do essentially. We do all the analysis depending on the different situations. So reality is that you can use the kernel techniques, but up to analyzing up to power 3. We use monotonicity formula for kind of heat function, but then from power 3 on, we need different techniques.
Okay, so next questions are from Stephen Watson. So he's asking, what is known about the regularity of free boundaries to time-dependent Stefan problems that arise by incorporating surface tension with the associated Gibbs-Thompson boundary condition, and then studying the free boundaries that emerge from the singular limit as sigma goes to 0, as the surface tension.
Good. Yeah, good question, very good question. I never studied much these kind of questions. In general, there are very few results about all these problems. So already our result that now we did in the Stefan setting, this very simple one phase, it is one of, so of course there will be many results about understanding singular points, regular points. Everything I said about, let's say, Caffarelli analysis, this blow-up analysis was done in the parabolic case. But how really things happen, for instance, there was a theorem by Caffarelli that said that if you take, in the free boundary for Stefan, if you take a C1 curve and you assume that you have a C1 curve of singular points, then this curve has to be stationary in time. So this was the only result essentially about this problem. So, which of course is it was a good intuition to say that singular point cannot propagate in time, but of course, who tells you that a singular curve of singular points, C1 curve of singular points exist to start with. So I think what we did here is the first kind of study which can, really analyze how singular points propagate. One thing that we use very strongly, though, is the connection to the obstacle problem. So the moment you lose this connection, these kind of techniques are lost. So I think the first question would be probably to try to reanalyze all these, going one step back and doing directly the analysis at the Stefan level. That's the only way to go out also of this one-phase Stefan problem. But okay, first we need probably to finish writing this already, which is getting a bit complicated. But it would be definitely a very nice direction to try to analyze what happens if you add more parameters into the game. And I guess the same is a bit the second question. He's asking also if one introduces hyperbolic effects, like by kinetic undercooling. To me, I mean, it's the same question. I need to go back to the Stefan setting. Here we really use a lot this kind of connection to the obstacle problem. And the part where we really use it is to get to expansion up to order 3, because then, as I say, the techniques gets different. And there we use monotonicity formula. So first one to understand what is the correct analog in the Stefan setting, and then we'll go on. But yeah, I don't know at the moment.
Very well. And I see there's a last question by Hector Changlara, and that is, for the parabolic problem, what would be the analog of the blow-up classification as singular points? Is there something similar to the stationary case available? And what about the persistence of corners?
Okay. Hola, Hector. Let's go by steps. What's the analog of blow-up classification singular points? So the analog is really the same as Caffarelli. So Caffarelli proved in the elliptic case that let's say quadratic rescaling, U of RT, let's say, sorry, R squared T, Rx over R square. So it's the same scaling as in Caffarelli. Let's say 0, 0 is a singular point. In the elliptic case, there is no time. These converge to a polynomial. P quadratic polynomial, P non-negative, Laplacian P equal 1. So the first blow up at order 2 kills completely the time. So the time you don't see it in the blow up. So that's what I wrote like here. The first term will be stationary. The time you will start to see it in the third order expansion, which is what we do. So what was known before our theorem is just that there is a C1 converge, I mean, like U converge to this polynomial P, and this polynomial P varies continuously in time. The unfortunate thing of this theorem is that while in the elliptic case, this tells you that the singular set is contained in a C1 manifold, if applied in the parabolic case, it will tell you that you are contained in a manifold which is C1 in space, but only C1 half in time. Because in time you lose, by parabolic scaling, you lose half of regularity. So it's only older continuous in time. So a priori, by the results available up to this work that we are doing, the singular set could have been of dimension larger than the regular set, because the regularity was very weak, was only older continuous. What we prove in reality here, so you see here we are in dimension n+1, so in parabolic dimension n+2, and we prove that the singular set is actually of dimension m-1. So it's actually much smaller in the parabolic case. But a priori before it was even larger. So that's about the analog blow up. So what this was known, and now we did the next order expansion. So actually we have an expansion up to C infinity here, but the expansion is different exactly because you don't have it's not a clean expansion as in the elliptic case. Now, the block is there something to stationary case? Okay. What about the persistence of corners? So okay, this is an important question that I cheated a bit. So what Hector is referring to is the fact that if you take the Stefan problem and you start with a free boundary at the time 0, which has a corner, like, so the ice at time 0 has a corner, then this corner will persist for some time. So it will take some positive time before the corner this starts to move. So I told you that you remember in the Stefan problem, the derivative, the speed of the free boundary is given by the gradient of the temperature. So this is moving. But if you have a corner, at the tip of the corner, the temperature will have 0 gradient. And so the corner will not move at that point. And actually, this will persist in time. So at that point, actually, the change of variable that I told you from u from theta to u, so this integration in time doesn't work. So in a sense, the point is that as long as the free boundary doesn't move, you don't even have that equation. The -1, you only see the -1 in the right-hand side the moment the free boundary starts to move. So let's say everything I said is at every point where the free boundary is positive speed. So if there is a corner, you need to wait a bit of time until the corner starts to move. Then once a point starts to move, it will never stop moving. And then everything I said applies. So the cheating that I did was that I told you that the Stefan problem was equivalent to the obstacle problem. That equivalence is true up to stationary points that first need to move. But once they move, then they're equivalent, the two problems. So yeah, thanks for spotting this small cheating that I did.
Okay, there seems to be no other questions. So thanks, Alessio, again.
Thank you. Thanks for inviting me.
And I guess I wish everybody a nice afternoon or a nice evening, depending on where you are. Oh, wait a second. Yeah. So, oh no, okay.
No, it's not
from Stephen Watson, but no more questions that I can see on the chat, neither on the question and answer sessions. Ok. Ciao Alessio, buona serata.
Okay. Ciao, ciao a tutti.